Well, good morning and welcome to physics class. We are finishing today the chapter on relativity. This is part of modern physics, as we said the other day. Modern physics started around 1900 or later. Classical physics started about 1400 or so. So this is more recent material. And the last section we're going to talk about today is general relativity. See, here's the limitation. Special relativity deals only with inertial reference frames. And on your review page, you have 2.1, Concepts, Special Theory of Relativity. Three things you should put on there. Two of them was from the last lecture, but I don't think I had you put them on there. According to the Special Theory of Relativity, the laws of physics are the same in every inertial reference frame. The laws of physics are the same in every inertial reference frame. You need to write that in, okay? And this is from the last presentation, so you might have it in your notes if you happen to be taking notes. Special relativity states that the laws of physics are the same in every inertial reference frame. Secondly, they tell us the speed of light is the same in every inertial reference frame. It's our absolute reference point. Every inertial reference frame has the same speed of light. Third thing is this does only apply to inertial reference frames. Okay, speed of light is the same in every inertial reference frame. And number three, special relativity applies only to inertial reference frames. General theory of relativity expands his theory to all reference frames. So non-inertial reference frames are now explained in general relativity. Now, we're going to be looking at general relativity generally. We're not going to do any math. We're just going to get some basic concepts and some applications, actually, okay? But general relativity applies relativity to all reference frames. And one of the ways he did this was by connecting gravity and acceleration. Okay, he connected gravity to acceleration. The general theory of relativity mainly states that acceleration and gravity are indistinguishable. Okay, you can't tell the difference between acceleration and gravity, and therefore you can take the laws of physics and apply it to an accelerating reference frame. You just end up with a kind of new gravity. And an example of this is the rocket, and they did a picture of this for you. Okay, so if you drop a ball on a rocket and that rocket ship accelerates, then the ball is going to fall. And you will not be able to tell the difference between let's imagine that this rocket is accelerating upward at 9.81 meters per second squared. You would not be able to tell from your math calculations whether or not your rocket has a gravity which has an acceleration due to gravity of 9.81 meters per second squared, or if you're in a rocket which is accelerating at 9.81 meters per second squared. Okay, you couldn't tell the difference from the physics. Now, if we were to live on a world where our gravity was actually a result of acceleration, there would be some things that would be different. But our theories would come out a little differently. But you couldn't tell the difference by the behavior of any particular object. Okay? So gravity and acceleration are indistinguishable, and that even has an effect on light. So they have this picture of this rocket, and you shoot a light beam, as the rocket accelerates, the light beam is moving in a horizontal direction at the speed of light, but in a vertical direction, it's just moving at the speed of the rocket. And if the rocket's accelerating, the light is also going to bend. Now, please note, to see this, the rocket would have to be accelerating fast enough so that you'd have a noticeable change in the brief fraction of a second that light takes to get to the other wall. Okay, so it's not very realistic, but it is theoretically obviously true. If you have a rocket ship which is accelerating sufficiently, then the rocket is going to move while the light is moving, is traversing that distance. Okay, so on 2.4 on your concept, this under concepts, gravity, acceleration, and light. So gravity and acceleration are indistinguishable. First step, gravity and acceleration are indistinguishable. Since they are indistinguishable, obviously there is going to be not only an acceleration effect on light that we saw with the rocket ship I just showed you, but gravity as well. Gravity will affect light because acceleration does, and gravity and acceleration are indistinguishable. Let me say that again so you can get it written down. Since acceleration and gravity are indistinguishable, and since acceleration clearly affects light, so does gravity. Therefore, there is a gravity effect on light. Okay? And that's 2.4 on your review page. Okay. So gravity attracts light. This is called gravitational lensing. We've observed this with the sun, with some distant stars, and with galaxies. So, especially during a solar eclipse, they're able to see this. You can't usually see it, but light that is traveling past the sun, like starlight that passes by the sun to Earth, is attracted to the sun and moves. This only happens to light that's close enough to the sun. Normally the sun is so bright we can't see it, but during a solar eclipse the sun is not bright and we can take pictures of the stars and observe them, and they're in the wrong places. They move. And we can, you can kind of tell where they are normally when the starlight's not passing the sun. It's on. When we're on the other side of the sun, the starlight comes directly to us. When we're on this side of the sun, it passes the sun, and we can actually tell the difference where they are. And galaxies, there are galaxies that we can observe that are large. And so light going past them from even more distant sources, like stars or galaxies beyond them, the light gets bent by the gravity of the galaxy. We actually observe this. Okay? So this is observed with the sun and with distant stars and galaxies. That's the answer to 2.5. Okay? So 2.5, the sun actually bends light coming from distant stars as they pass the sun, and galaxies bend the light of more distant stars and galaxies as they pass the galaxy. Okay, so get that on your review. Sorry, I forgot to click and move it to the next slide. Okay, so let me just real quickly, gravitational lensing. This is where gravity attracts light. We observe it with the sun, with stars that are past the sun. As the starlight comes past the sun, it gets bent. We observe it with galaxies, doing it to more distant objects, and that's 2.5. Sorry, I went through that all verbally and didn't have the words on the screen. And so if you need to go back and review that section, I apologize. I didn't realize I hadn't clicked the button to move it forward. All right, let's talk about black holes. Black holes have such strong gravitational fields that light cannot escape from them. And this is term 1.2 for you. Now, there's a lot of different theories about black holes. They think these are collapsed stars. We don't know for sure. These are somewhat theoretical, though they think they have actually identified actual black holes in the universe. But these holes have very, very, very strong gravitational fields, so strong that light cannot escape from them. All we get is actually like a byproduct of their being sucked into the black hole, and you get, I believe, they're X-rays that come out of them, but no light comes out of them, no light gets past them. They're just black hole. Nothing else gets past them either. Any kind of matter that comes past a black hole gets sucked into the black hole, making the black hole even bigger, making its gravitation even stronger. So black holes just seem to grow. They also think these may be responsible for holding galaxies together, but I will mention this is a little bit like we talked about with the Big Bang Theory with dark matter. Black holes are not dark matter. Black holes are physical. We can't observe them in the sense that we could observe them if there had any tool to observe them with, because they're there. But we have to kind of observe their byproducts because they're so powerful. Most of our normal ways of looking at things don't work. Light doesn't work as our normal way of seeing things because they suck it in. But we can observe kind of the effect of that. So a black hole, black hole is simply just call it a collapsed star that has such a strong gravitational field that even light cannot escape from them. Some other evidences of general relativity: the precession of Mercury's orbit, and Mercury gets affected by various gravitational forces, and it changes Mercury's orbit slightly. And in order to completely explain all of the variations in its orbit, you have to include the idea that there is some of this is from general relativity. And I don't know any more details of that other than they say it has to be explained using general relativity. They have found that clocks are affected by gravity. So time is affected by gravity. Really bizarre concept. Technically, a clock in the basement of a skyscraper will move slower than clocks on the roof. They actually have verified this using really, really sensitive atomic clocks. This is very relevant to Russ Humphreys' white hole cosmology. It goes back to black holes we were just talking about. Black holes, because of their intense gravity, actually stop time. Russ Humphreys has a white hole, which is the opposite of a black hole. Everything's going out rather than in. But he also has a horizon, it's called, where time stops. And this is based on this idea there's a relationship between gravity and time. Gravity can actually affect time. And this is part of general relativity. And then there are light wavelength shifts, red and blue, that have to do with the gravity of the object that's projecting the light or absorbing the light. And so they've actually tested general relativity. This is a bizarre theory, but it's really fairly standard at this point in time. There's a lot of evidence supporting general and special relativity. I'll just toss it out there. You will find some conservatives, Christians, etc., who deny relativity and argue that some of the evidence isn't there. And there certainly are debates about how to interpret some of these things. William Lane Craig's an apologist who doesn't like the interpretation where time is actually twisted and runs differently. He doesn't actually, he says there are other interpretations. But this is the basics of it. Okay. And so I kind of gave you an overview. Relativity is something that definitely is part of modern physics, something you should be a little bit familiar with. Hold on to that review page. Don't send it in because there is a summary coming next week, or the end of this week, sorry. So then you're going to need this review. So hang on to your review. All right, tomorrow we start chapter 28.